So we're gonna, this you can get, the first one you can get an actual number for. This one you're just gonna write an integral expression. And these you can actually get numbers for, but it may help to draw the graph if you can figure out what that looks like. And I'm gonna upload the video from last hour.
So the first one. I have a loop. I have a loop to R squared. Decimals. Is that all it is?
Yep.
Become minus? Yes, it's below the x-axis.
What's that third one?
This is
Negative 3 to 2. Oh,
no,
that's a
this,
that's a that one. Okay. So, Alec,
yeah.
how are those poems going?
Well, I did them in the LSC this morning, so.
Did you?
Yeah, they're okay.
Smart play.
I had a second period. So does it just maybe one, like,
Cool.
you know? For this one, yeah.
Yeah, this one is just one.
It's just the graph of x minus 2.
4 area. 8. 12. Oh no, look at what happened to this poor white chalk. Disgusting. Cool. Have you been looking at the Discord throughout the day or the night?
I did. Some Shouldn't it be 16?
Look at this folder.
Larry's looking so unvandalized today. Just wait.
You said something.
I just didn't know his existence was there yet.
Dang. Well, Larry's gonna be vandalized.
Larry's not going to be angry today. right?
What is, what?
It's supposed to be teardrops.
Something different.
Fine. Larry's pissed off again.
Begin.
It just looks like a spider.
So on the first one, we just used the 1/2 pi r squared, is that right?
Yeah.
So since the radius is 3, we have 1/2 pi r squared is going to be 9 times pi.
Yeah.
And the next one, the idea is, if we're talking about area, we don't want to count this as a negative and like cancel each other out. So there's 2 ways you could do this. You could say the true area will be the integral from 0 to a of f of x minus the integral from a to b of f of x, so that this is going to end up being a negative number, which we want to make positive. Or you could go 0 to b of the absolute value of f of x dx. And this would be more if you had a calculator active problem, because in general doing the absolute value isn't really doable unless you've got the calculator. Otherwise you're going to have to do something like that. This, if you remember, now it's a theorem that all continuous functions are integrable. So we can find the area between a curve and the x-axis if it's continuous. It turns out we don't need that much sometimes. Some discontinuous functions can be integrable. If they're only, if we have like a, what would we call it, discontinuity, and I'm blanking on it now.
A jump?
A removable discontinuity, where just one point is the issue. So, and
Like
jump
that.
we can in this case too. So what we have here is that this is our graph that's going to be 1 everywhere to the left and -1 everywhere to the right. And so it's undefined at that point 0, but so we miss that area under the point 0, but a point has no size, so we're not missing anything.
Well, so with that argument, couldn't you also call like something an absolute max in those cases, where it's a jump discontinuity?
So now clarify what you mean by absolute
So if
max.
you can argue that you can still find the area because it's negligible, couldn't you call like something that doesn't include a point, like the open circle, an absolute max?
No, because the problem there is, you know, we don't have a largest value there. So it's not that the problem isn't so much what happens there. The problem is that the density of points is we can't choose the point right next to it.
Right.
Because there isn't one.
Yeah.
That's the issue there. Rather than how big is that point.
Yeah.
Because we can't say that the maximum value is whatever that number is, because it never reaches that. And there's no way to say it's the point that's right below it, because there isn't one. Because they're so dense, there's so many of them. So then we can say this area is going to be 1, but since it's below the x-axis, we'll count it as -1, and so we'll get that this integral is actually 1, using an area argument. And if you see that you can factor this, so that's going to be x minus 2x plus 2. When the x minus 2's cancel, there's a hole in the graph there. So we get this straight line with slope 1 and y-intercept 2. We're going from 0 to 4, and at 2, we have a hole in the graph. Now, that's not really an obstacle, because you just subtract off 0 from that area under the curve there. And you could do that, I mean, you can do an area argument. We can say there's a rectangle that's 4 by 2, and a triangle that's, we plug in 4, we get 6, so that's going to be 4 by 4. Is that right?
Yep.
So that's going to be half of 4 times, is that another 8 already?
Yeah, it is.
So it's going to be 16. Okay. Now, what's interesting, food for thought, where we're headed in this class, is what happens if we have something like a vertical asymptote. So if, if we were going to say, suppose we wanted to take the integral from -1 to 1 of 1 over x dx, and you've got a vertical asymptote there. So you get, or let's make it 1 over x squared, so we'll just make it be the volcano graph. So suppose we are doing this, and we want to know, can we find that area between the curve and the x-axis with that kind of infinite chimney kind of thing? See what the question is that I'm asking? So we see that we can integrate over some discontinuities, but not every discontinuity. So we in certain cases, can integrate over that jump discontinuity, over a removable discontinuity. Can we integrate over a vertical asymptote? And the answer is sometimes. It depends. And we'll talk more about that. We're not ready to do that today, but it's kind of an interesting thing to consider. Okay, to be continued, right? So questions on the homework? Any of those you'd like to see clarified?
Yes. On homework, I like the review.
Review?
The review. So it was number 6. It had to do with the horizontal, not the horizontal, the slant asymptote. I think we got confused on where that came from.
Yeah. So do you remember the original function?
Y equals x squared minus 2 over x.
So it's been a while since we've talked about slant asymptotes, but back in our AP prep days, what we said is if you have a rational function, a polynomial over a polynomial, and if the degree of the numerator is 1 bigger than the degree of the denominator, that will lead to a slant asymptote.
That's why you need one division.
Yeah.
I was right.
So as x goes to infinity, this is going to go to infinity because the degree of the numerator is greater than the degree of the denominator. But it will go to infinity in a very predictable way. So as this gets really, really big, this is going to look more and more like a straight line. Now you can do long division. This one you can actually, because there's a monomial denominator, it's actually a little easier to just call x minus 2 over x. Now as x goes to infinity, this is going to become less and less of a consideration, which means that the curve, which is definitely not a line, as you go way out to the right and left, is going to look like the line y equals x. So that's our slant asymptote.
So that's just if the degree of the top function is 1 more than the bottom?
Right.
Okay.
Want me to keep going, or is that enough?
That's
good.
That's all. we got
Okay.
confused
Yeah,
on.
it's been a while.
Yeah.
Anything else?
Yes, there is. One more thing. 2 more things. So it says the distance traveled by a projectile. An object is shot straight upward from sea level with an initial velocity of 400 feet per second. And assuming gravity is the only force acting on the object, give an upper estimate for its velocity after 5 seconds have elapsed. Use g equals 32 feet per second squared for the gravitational constant.
So it's really a negative 32.
Yeah.
So that's our acceleration, right? And we're trying to approximate
The upper estimate.
the upper estimate.
So, yeah.
So we are going to integrate this to get velocity, I believe. Trying to think how we're going to do this, because we haven't really, I forget what we know and what we don't know at this point in time. Upper estimate.
It's pretty much just the height equals, I don't know, I remember the answer was something like, read the base, you get multiply 5 times negative 32 and subtract 100 by that. That was your answer. It was 240, I think.
What section are we on?
But I can't remember.
Because we can certainly integrate it. Yeah, I'm not sure how exactly they want us to do this. And we know our initial condition, which is going to make that, and we plug in 400 when t is 0.
Ten.
It's just that.
Yeah.
Wow,
Oh.
we checked that one out. We're good.
That upper estimate part is the part that's throwing me. Why,
Yeah, I
why
didn't
would
really-
we call it that?
I didn't know how to do that, so I checked the answer.
And the answer's just that, but I don't know why they called it. And that's why we also start 29s, because the words upper estimate are kind of a weird thing, we don't know what it means.
I think 29 makes a little bit more sense, because after 29, there was like, you go by the beginning of the month and the end of the month. Whereas like this one, it's just like,
Yeah, that seems like a weird way to frame it.
Yeah.
Yeah, I'm not sure why they would call that upper estimate. So I think that's pretty much exact. I don't know where the estimate part comes from.
Which is why we started that bad boy.
Yeah. Anything else?
We're good.
All right. Let's see. We are going to talk about definite integrals and anti-derivatives.
Oh, no, 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 sorry. We actually- Well, derivatives are better, but we can't complain with some of the integrals we were supposed to be. Granted, now it's gonna be like 10 times harder.
So we said our definite integral is where we take the limit as n goes to infinity of f of the sum I, let's go, the n goes to infinity, I goes from 1 to n of our Riemann sum, f of c sub I times delta x. And that is what we're defining as our definite integral. And we understand that this is not a true area, it's kind of a net area. And if we want the true area, then we have to be careful and make sure that our curve is above the x-axis, that our limits go from small to big. Okay, so the rules for definite integrals, and these rules all come back to the way this definite integral is defined. So one is that the integral from a to b of f of x, if we switch the order and go from b to a, then how does that affect the integral? Yeah, so it makes it a negative of whatever that was. And that goes to how we figure out this delta x, because this delta x is b minus a divided by n. And so if this, whatever it is, when we subtract these, if we change the limits, then it switches the order of the subtraction, and that means it changes that sign. Similarly, we know that the integral from a to a of anything is 0 because it's the area under the curve of a single point, or again, the way we define our delta x is by taking the upper limit minus the lower limit divided by n, and that's going to be 0. And so we're just adding a bunch of zeros. We know that, some space here. So we can say that the integral from a to b of f of x dx of c times f of x dx is we can just pull that c out. We have this additivity property. So if we take the integral from a to b of f of x dx, then we could say that's the integral from a to c of f of x dx plus integral from c to b. And it doesn't matter, I mean, it makes it seems really logical why you would do this. Perhaps if you had, you know, a, b, and then maybe c was some interior point, but it's not restricted to c being an interior point. I mean, crazily enough, you could take c to be there, right? I don't know why you'd want to do this, but you go integral from a to c plus that integral from c to b would subtract that part off. So kind of a weird way to think of it, but this property is integral from a to b of the sum or difference of functions. Just split them up. And whether you're adding them or subtracting them, you do the same thing. Now, our book makes more of an issue of this, which takes a little bit of thinking, but I think seems reasonable. So this is number 6, which is our max and min inequality. So the idea is if you say little m is the absolute minimum of f on that interval from a to b, and capital M is the absolute maximum of f on that interval from a to b, then we can say, I'm going to put an inequality around this. The integral from a to b of f of x dx is going to be bigger than the smallest value times b minus a, and less than or equal to the biggest value times b minus a. So I think if we look at it visually, it makes pretty good sense. So suppose we say our function f looks something like that. And here's our a, and there's our b. And so we look here and we say, this y value over here is our absolute minimum of that function on that interval. And over here is our absolute maximum of that function on that interval. Then, see the area, so our integral from A to B is, we're talking about the area between our curve and the x-axis. And what this little m times b minus a is the area of this rectangle that has height at minimum value and width b minus a. It's the area of that rectangle. So it seems quite reasonable then that, the integral would be bigger than that, bigger than or equal to. And likewise, the capital M times b minus a is the area of the rectangle that has height at maximum value, the absolute maximum of the function, and width, b minus a, the length of that interval. So it gives us like a bound, a lower bound and an upper bound for what that integral could be. So I think it makes good sense. You just don't see it very often, but our book makes an issue of that, as they do here too. They call this their domination, which is kind of a weird way of talking about it. So the idea is if f of x is greater than g of x on the whole interval from A to B, and I think it seems it's completely reasonable to say the integral from A to B of f of x would have to be greater than or equal to the integral from A to B of g of x.
Common sense.
And then similarly, if f of x is always greater than or equal to 0, yeah, then the integral from A to B of f of x must be positive, must be greater than or equal to 0. Okay. So we can play little games to make you use some of these relationships. So suppose that the integral from -1 to 1 of f of x is 5. The integral from 1 to 4 of f of x is -2. And we can ask a few questions about that. You can say the integral from 4 to 1 of f of x. The integral from -1 to 4 of f of x. Integral from 1 to 4, or we can find, I guess, the integral from, yeah, 1 to 4 to f of x.
These used to be so hard.
The integral, it's funny how far we've come. -1 to 1 of f of x plus 2 dx. So 4 to 1 you said was how much? 2. That was -2, so switching the limits changes the sign. Integral from -1 to 4 would be 3, because you just take the 5 plus -2. So 2 times the integral from 1 to 4 is -4. Integral from -1 to 1 of fx plus 2 is going to be
Yeah, 9, right? Because we just separate them? Or-
You can separate them, yeah.
You get the integral from -1 to 1 of fx plus 2, so 5 plus.
Yeah, I remember doing that a lot.
That we said was fine.
Yeah.
And this you
That's
can
what we did.
either integrate or even think visually. It's horizontal line from -1 to 1. So we get to 9. Okay. To average value of function. Kind of a cool idea. So the idea is kind of cool. I mean, we know how to find the average value of a finite number of numbers, right? You add the numbers, so you would say you add the n numbers and you divide by n, and that's what we mean by the average of a finite number of numbers. So the idea of an average value of function, you got to stretch your mind a little bit. So you're going to take all of these infinite number of y values, add them all together, and divide by the number of numbers. So it's an infinity over infinity issue, and the question is then how do you resolve it? It's going to have to be a limit in there, and we're going to play around. So here's kind of a neat way of conceptualizing it. So let's suppose that you imagine taking n values in between here, and you're going to evenly space them. Okay, so you're going to take f of x of 1 plus f of x of 2 plus out to f of x of n. And you're going to divide that then by the n. Now we're saying these x of i's, so I'm going to say x of I minus x of I minus 1 is going to be our delta x, which is going to be b minus a over n. So it's easier to conceptualize if we imagine we space them out evenly. Okay, so there's our average. So since we're going to do this, we can solve for this, because this is really like 1 over n times the sum, I going from 1 to n of those f of x of i's. So let's solve for this 1 over n in terms of delta x here. We're going to try to create something that looks like a Riemann sum. Okay? So can we, if you visualize it, if I leave the 1 over n here, how do I get rid of that b minus a? Tie it to the other side, so that's going to look like what? I want to keep the 1 over n because I'm going to replace that.
Change an x over
Thanks. That okay? So then I'm going to replace this 1 over n by that. Now this is a constant, I'm gonna bring that inside. Think of this like a huge distribution problem, right? Because this is a bunch of things added together. Just gonna bring the delta x, I'm gonna leave the 1 over b minus a on the outside. So we're gonna make that look like 1 over b minus a, and now our sum going from 1 to n now looks like f of c sub I times delta x. Is that okay? Oh, we've seen that before. That is our old familiar Riemann sum. F of c sub I times delta x, that's a Riemann sum. And we know right now we're talking about a finite number of n, but we said we really wanted this to go to an infinite number of values. So we'll throw a limit as n goes to infinity. And this will become, well, we can factor that 1 over b minus a out. And this limit as n goes to infinity of that Riemann sum is our definition of a definite integral. It's the integral from a to b of f of x dx. Okay, cool. That's how we find the average value of a function. So you're right, we did take a limit. So let's see. Let's say the mean value, I'm going to give you the theorem first. So the mean value theorem for integrals. If f is continuous on the closed interval from a to b, f is continuous on that interval from a to b, and at some point c, in that interval from a to b, f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. That is, the function has to equal its average value somewhere on that interval. So there's kind of a nice visual that goes with this. So if we draw our function, so here's our generic function, f of x. And we're looking at the interval from a to b. Then what this is really saying, if you multiply this b minus a to the other side, you can see that f of c times b minus a is equal to the integral from a to b of f of x. Which means this, which is that area between the curve and the x-axis, must equal, here's the b minus a is this length right here, times f of c, which is, I don't know, somewhere in here is our f of c. So the idea is there is a rectangle that has height, the average value, over that interval, where the area of that rectangle is the same as the area of the curve. And this is saying that the function must equal its average value somewhere on that interval. Reasonable? Okay, so let me give you an example then. So find the average value. Find the average value of f of x equal to 9 minus x squared on the interval from 0 to 3. And then I'll ask the question, but we've already kind of answered it. Does f of c equal the average value on the interval? And if so, find that value c. Does that make sense? Put it at the board. I like that idea.